Hey everybody, we got a triple summation going on tonight, and we're looking for a positive integer solution. The natural numbers are the same thing as the positive integers 1, 2, 3, and so on. Okay, and again, notice folks, x appears as in the upper limit of two of the summation symbols. Now, we can establish an intermediate result that's going to make this task a lot easier. Notice that, well, I tell you what, I'll just work a concrete example here. Each of the summands contains the constant 1, which is a little strange. But let's look at this concrete example where we're going from I equals 3 to 7, and we're trying to add up that many 1s. Now, notice that that would correspond to 1. And the very first, that would correspond to I equals 1, right? Now, 1 has no dependency on the index of the summation. But 1 would correspond to I equals 3, and then plus 1, another plus 1 would correspond to I equals 4. All right, and we can just keep going. We have to go to 7, right? So we have plus 1 corresponds to 5. Another plus 1 corresponds to 6, and another plus 1 corresponds to 7. Okay, so what do we have there? We have 5 1s here. Now that's 1 more than 7 minus 3, right? So this is equal to 5. But notice that's equal to 7 minus 3 plus 1. Right? And so that's the only thing about this that could be overlooked, I suppose. Again, you have 7 minus 3 here, which is 4, but if you count out your indices, you actually have 5 occurrences of the summand 1, which sums up to 5, and that's equal to 7 minus 3 plus 1. And so that's how this result works for any pair of positive integers. Okay? Now, so armed with that result, let's see what we can do with the problem. Okay, so we actually apply this result you see 3 times. We have 3 summands, so we can apply this result 3 times. We're just using variable upper limits, okay? And so again, this 1 that you see here is exactly the 1 you see up here. This 1 that you see here is exactly the 1 you see here. And this 1 you see here is exactly the 1 you see here. So this little lemma actually gets used 3 times to help knock this down to something manageable, something tractable. All right. Now, what happens here, folks? Well, I'll just write it directly underneath. This, all you're left with here is x squared, right? Now, right here, you have x minus 3 plus 1 is x minus 2. So that would be minus x plus 2, right? I'm trying to keep it lined up sort of, folks, but this part right here resolves to minus x plus 2. If I did this right, x minus 2, then you negate that, you get minus x plus 2. Now what about right here? 117 minus 6 is 113. Or no, excuse me, 111 plus 1 is 112, right? So this would be minus 112. It still equals 0. And remember, y'all, this is the problem we were asked to solve. Just recopied it. Okay, now what does this resolve to? Let's see. We have x squared minus x, and then plus 2 minus 112 is minus 110, right? And then we're looking for factors that will create a negative coefficient of x, negative 1. And folks, this, with some trial and error, you will see that this is equal to x minus 11. The linear factor x minus 11 times x plus 10. And do recall we were looking for a positive integer solution. And so we get a positive integer solution. I'll write it over here. X equals 11. And folks, you can check that on your own if you want to, but it does work. Now notice we would have gotten an integer also x equals negative 10, but notice negative 10 would not work very well right here. If you put a negative 10 right here, you have I equals 3 to negative 10, which I don't think makes much sense in summation notation, right? You're usually thinking of the summation index increasing. So we're talking I equals 3 and x equals negative 10 would have been a possible solution, but it would not make sense for this particular sum, and it would work here. And you can check if you want to, but I don't think negative 10 is a solution. But in any event, we were just looking for a positive integer solution to begin with. And so the answer to the question is x equals 11. And it's a fairly quick computation if you want to plug that in and see if it works in this equation. Thank you for viewing.